Hello Internet! Last video, we built c0.js, a tiny C-ish compiler with a control flow graph that lets us run gotos in WebAssembly. But I skipped over something. Look at this expression. C0 cannot compile it. It cannot represent it. In C0, our basic blocks are still chunks of C code. We compiled control flow between blocks, but the code inside the blocks is just raw source. And source code hides control flow inside expressions. Today, we fix that. My real C compiler doesn't use SSA. I built it without an IR because a single-pass typed AST design, aside from the occasional irreducible control flow, fits C and WebAssembly almost like a glove. But every other serious compiler uses SSA, and I want to know if I'm missing something. So I'm building 5 toy compilers, layer by layer, to learn SSA from the ground up. At the end of the series, I'll decide whether to retrofit it. TAC makes intermediate values explicit. TAC by itself actually makes our compiled output worse. We fix this in C3 when we do optimizations. 3 address code. The whole idea is in the name. Every operation has at most 3 addresses, 1 destination, 2 sources. That's it. Take this expression. As an AST, it's 1 statement with a sub-expression. As TAC, it's 3 lines. Notice what just happened. The result of I times 2, that intermediate value that existed for a moment in the tree and then vanished, now has a name, T0. It's first class. We can talk about it, point at it, ask questions about it. The intermediate value was implicit in the tree. TAC makes it explicit. Here's a whole TAC instruction set for C1. 5 classes. Const puts a literal into a virtual register. Binary op and unary op support the same operations the AST had, plus, minus, times, comparisons, but require explicit virtual register values rather than sub-expressions. Copy values of value over to a new register. Call calls a function and binds the result to a virtual register. Quick aside, when I say virtual register, I just mean a named slot that holds a value. Terminators, branch, branch if, return, unreachable, are identical to C0. 3 things this format unlocks. First, evaluation order is easier to reason about. We can see whether f runs before g simply by running over the flat list and seeing which comes first. Second, side effects can't hide. A call is 1 line, not buried 7 levels deep in a tree. Third, we can ask what's alive here, point at any line and list which variables might still get read. We won't use any of these today, but they will make our future work in C2 and C3 a lot easier. From AST already exists from C0. It's the same shape. Walk the AST, and build blocks. What's new in C1 is that we now lower all statements and expressions the same way we lowered just control flow before. Each expression lowers to a function call that emits its TAC and returns the name of the register holding the result. The parent expression uses that name as an operand. So let's go through an example. We start at the top, a binary node plus. We need to lower its left side and its right side. Left side is total, just a variable. We get a name back. Right side is I times 2, another binary. We recurse into it, lower I, lower 2, emit T0 equals I times 2, return 0. Pop back up. Now we have total and T0. Emit T1 equals total plus T0, return T1. 3 instructions. The implicit became explicit. Now going back, we have a function called intoAST that takes our CFG and lifts it back to an AST. But it doesn't do everything you might expect. At least in C1, it does not reconstruct expression trees. The TAC, T0 equals I times 2, T1 equals total plus T0, doesn't get collapsed back into total plus I times 2. That's a harder problem, and we will solve it later, likely in an optimization video. Instead, intoAST emits 1 AST assignment per TAC instruction, wrapped in the while switch dispatcher form we saw in the last video. Each TAC instruction becomes 1 assignment with 1 node deep right-hand side. Each terminator becomes a state update plus a break. The whole function becomes 1 while switch loop with each basic block as a case. So why bother going back to the AST at all? Why not just generate the WebAssembly directly from the CFG? 2 reasons. 1, WebAssembly itself is a structured format. It has if, loop, block, but no goto. Going through an AST means we're targeting WebAssembly's actual shape instead of fighting it. And incidentally, the C0 WebAssembly emitter already handles those constructs, so we keep it unchanged. 2, the AST is easier to inspect than the CFG. The AST maps more directly to actual C syntax, which makes it easier to convert back to source and see what happened. Okay, so remember this? In C0, this couldn't be compiled. Here's what C1 does. When from AST sees a logical AND, it doesn't emit a binary op. It splits the basic block. It evaluates A, branches on it with branch if, calls F in one branch, skips it in the other, and then joins back up. The expression literally becomes a small control flow graph. The mechanism we use for short circuit AND is the same mechanism we use for if-else. Two basic blocks joined by branch if. The short circuit was implicit in the AST. Now it's explicit. And it's the same primitive we already had for statements. Logical OR is a mirror. The ternary operator is the same shape. Branch, two arms, and merge. Three operators that C0 couldn't compile. C1 gets them all from one structural change. Okay, so what did this actually cost us? The same program compiled by C0 versus C1. C1's output is bigger. Why? More WebAssembly locals get declared, more WebAssembly instructions get emitted. Now, what about runtime? On a naive WASM engine, say an interpreter, C1 is probably meaningfully slower. More instructions mean more dispatch. More locals mean more load and stores. There's no way the extra work is free. On optimizing engines like V8 and SpiderMonkey, the hit is smaller than you'd imagine because those engines run their own optimizers using SSA-based IR, so a lot of the runtime cost folds away at JIT time. But it's strictly worse than what we had before. This is why TAC alone is a step backward. But it's a step backward you have to take because the things TAC make explicit are what the next passes operate on. In C3, I plan to add at least 3 short optimizations: copy propagation, dead code elimination, and constant folding. After those, the optimized TAC output is likely smaller than the original C0 output because the optimizer can see across statements that C0 treated independently. Okay, so let's recap. TAC made intermediate values explicit. We got logical AND, logical OR, ternary operator, essentially for free. We paid a good deal in code size to set up the next move. Okay, so next video, C2, we go full SSA. Because TAC by itself still has something implicit that we care about, one name can mean different values at different points in the program. Every assignment to a variable changes the value. SSA makes it explicit. Every write gets a fresh name. Each value has exactly one defining instruction. And once each value has a unique definition, the optimizations in C3 become much easier. Yeah, I hope that was better. I hope that was better. Okay, until next time.